All right, so I think it's 12 o'clock and we can start. Yeah, good afternoon once again, and welcome to Newtonian Mechanics Lecture 2. Yeah, today we will be looking at the second unit of the model. Another unit, we have the title as Newton's laws of motion. So that is the topic that we'll be discussing today. So we are hoping that by the end of today's interactions, we should be able to explain the nature and then concept of forces, then state and then explain the three laws of motion proposed by Newton, then also explain the relationship between force and then motion, and then lastly, we'll look at the difference between force, mass, and weight. If we still have enough time, we'll solve some simple sample questions relating to whatever discussion that we'll have today. So in brief, this is what we should be expecting at the end of the interaction. Yes, is my voice clear and loud? Because I don't trust my internet here. I don't know. So can you
Loud and
confirm?
clear.
All right.
Can hear
thank
you say. Right.
Okay. All right. So as we started last week, and I told you the nature of the course, and which I said the purpose of this course is that we are limiting ourselves to the Newton's laws of motion. We are describing particles movement based on the three laws that Newton proposed. Okay, so as you and I know from the vector quantities last week, we established that force is a vector quantity because it has both magnitude and then direction. So we want to see the aspect of force in motion. So when you talk about motion, we have two aspects. That is, we have the dynamic part of the motion and then the kinematics part of the motion. Now, the dynamic part of the motion has to do with the cause of the motion, which we will be looking at the force. So though we are talking about motion here, but we are not looking at the two aspects, that is the kinematics. The kinematics is still like describing a particular motion without looking at what caused the movement. But we want to take into consideration the thing that caused the particle to move, which we'll be talking about, the force. So the force here is the foundation of Newton's laws. Now we'll talk about the first law, the second law, and the third law. Okay. Now, when you recall from your general physics, the first law that was proposed by Newton stated that that law at times you coin it as what the law of what everything do, whatever thing it tends to do. Okay, so that is a layman point of view. So whatever that you are doing at normal circumstances, you're supposed to keep on doing that thing. So that was the basis of Newton's first law. So the law stated that when a particle is, or when an object is at rest, or if the particle is in motion, the particle should continue to be at rest, or if it is moving, should continue its movement, unless it is being acted upon by an external agent, which we call the force, that would trigger the particle's motion and then the direction at which it is moving. Okay, that is the first law. So the first law basically says that whatever thing that you are doing, you should keep on doing that thing. Time shouldn't come that we are tired. So as we started this lecture at normal circumstances, we should have this lecture continuously. We should just continue without stopping. So we shouldn't have instances with network problem or lights out or certain things that we might log out from this meeting, or we call this meeting to an end. Okay, so once we started, it should be there forever. When we are not also doing it, we shouldn't start. Okay, so let's get the definition down. So we're saying that Newton's first law of motion. So we are starting with the first law. Don't do that. Okay. So when an object is at rest, should continue to be at rest. Or when it is in motion, should also continue to move in a straight line with a constant velocity, unless it is being at that upon by an external force. To change its direction and what speed. Okay, so since I use velocity, let me say velocity. Okay, so this is the first law, and as I explained in its simplest form, so let's say you have an object that is lying down here. So you don't expect this object to change its position. Changing the position is by moving from where it is to any other location. Okay, so if you also have something that is also moving, you don't expect that thing to stop moving. It should continue to be moving at the same time, the same space. Okay, so what he's trying to say is that at normal circumstance, when you put something down in your room, you don't expect that thing not to be there at the time you need it. And that makes sense. So assuming you put something in your room and nobody comes in to pick that thing, so anytime you want that thing and you go back to wherever you place it, you expect to find it there. But at normal circumstance that you go in and then the thing is not there, it means that either that thing is being picked by somebody else, which is a third person to that thing. Okay, maybe a thief, it can be a wind. A wind can carry that thing away from where you place it. An animal like a pet in your house can carry that thing away from where you kept it. So those things are external materials that may cause a dislocation to that particular object. So that is what the law is basically telling us. So in short, we can always say that every object continues in its state of rest. Okay, you can still restate the law that every object continue its state of continues its state of rest or uniform motion in a straight line. In a straight line, unless it is compelled by an external force to change the state. To change the state. To act otherwise. To act otherwise. Okay. So you can restate the law this way, which means the same thing. Now this means that the particle that is moving in a constant speed has no acceleration. Okay, so it means that any particle somebody on up or somebody is
Sir.
Yes, Samuel.
Please, uniform in a straight line unless it is compelled by an external. It is force or force?
It's force. It is clean. External force.
Okay. Okay.
Thank you. Compelled by an external force. Just give me some few minutes.
This means, not this means, this means.
Right, so let's proceed. So we're saying that this means that the particle in a constant speed has no acceleration. So you can really take note of this. So once the particle is moving with a constant speed, it means that the particle is no accelerating. Okay, since we know that acceleration is a change of what velocity respect to time. So once you change direction, there is an acceleration, but the velocity of the speed of the particle can still be the same thing. Okay, so for instance, if a particle is moving around a circle with the same or uniform velocity, you see that the particle is not increasing the velocity, but that doesn't mean that the particle is moving with a constant velocity. It's going to change. So what I'm saying here is that if this is my circular path, like a roundabout, you and I know that velocity is a vector quantity. And once it's a vector quantity, once you change the direction, so let's say if the particle is at this point, so if the particle is at this point, then the velocity is going to move in this direction. Now, if the particle finds itself at that point, once the velocity will be changing, it means that it will be pointing down. So you see that the direction has changed. And once there is change in direction, it means that there is an acceleration. It doesn't matter whether the person or the particle that is moving around the runabout moves with a constant velocity. Okay. So once there is change in direction, there is an acceleration depending on the particle location on the circular path. Okay. So the particle can be moving with like 2 meters per second in either positions, but because of the direction that it is keep on changing. So if here is 2 meters per second, 2 meters per second, when it was here, the same 2 meters per second here, you see that the velocity is constant. But once the direction has changed, it means that there is what? An acceleration there. Okay. So a particle can move with a constant speed in a roundabout, but still accelerate. So that's one thing you should take note. Now, this acceleration will happen when there is a force. Okay, so since we are saying that, this means that the particles constant, the particle moving, there should be move here. So this means that the particle moving at a constant, it should be moving here. Moving at a constant speed has no acceleration. So normally all the moving bodies that we know, when we bring them to a rest, okay, it means that we are trying to impose some forces on them to bring the moving object to a rest. So any moving object that comes to a rest must be some force being applied to it. For instance, a car that is already in motion, before the car can stop, then there must be a brake applied. Then when you apply the brake, there is a force. So that force will be in the form of what? Decelerating the car. So we'll call it like a retarding force. Okay. So there must be a force applied to either move the object to accelerate or to also bring a moving object to a rest. Now, the tendency of the body, the tendency the tendency of a body or object, a body, or let me put the object there. So here, when we are using body or object or particle, it's just like anything that you are studying. So you can refer them to a particle, a body, or an object. So the tendency of an object or a body to remain in a state of uniform motion a state of uniform motion. State of uniform motion in a straight line is what we call inertia. Inertia, and inertia basically means mass. Okay, the inertia of an object talks about the mass. So if the object has a larger size or a bigger mass, it finds difficult to move by a force. So when you apply a smaller force to a smaller object, you can see how the object will move. But if you apply the same amount of force to a larger size mass or object, you also see the movement of that object. So you see that the reluctance of a body to move depends on the size of that object. Okay. And we can bring it back to our day-to-day life. When you look at these vehicles that we have, we take these long vehicles, the articulated vehicles. You see they are having a longer mass. You see the kind of speed they move as compared to these small vehicles. You see their size and then how fast they can move as compared to the long vehicles. Okay, so the mass impedes the motion of the object. So it finds it difficult to move fast because of its sizes. So that is the meaning of the inertia. So, yes.
Sir, please, I have a question.
All right, come with your question, please.
Can we also call the tendency of an object to remain at its position or at rest inertia, or only when the object is in motion?
Oh, no, it can be. What I'm just trying to say here is that the inertia is just a mass of the object. So the inability or the relaxation of the body, when you subject a force or you push something, the thing does not just respond directly to the force that you subject, but it feels some reluctance. Okay, and that relaxation or realization of the body is as a result of the force that it possesses. The mass that it possesses. Unless the applied force overcome the mass, because when you are writing a force, we normally say a force of an object is proportional to the acceleration, where the constant is the mass. We write it as this. So this is a force. Okay, so you can see that the force depends on the mass. If we want to make m the subject here, you can say m is equals to force over a. Now we are talking about movement, which is about the acceleration. The acceleration causes the motion of the object. So if the mass is great, they are inversely proportional. The bigger the mass, the lesser or the smaller its motion or movement. So if it also has a higher acceleration, it means that it should have a smaller mass. So it's not about the body moving or being at rest, but it's just telling you the response that the body will have to a force. So just as I was saying, if you have an object which is small and this has 5 kg mass, and then like a bag of cement, which is like 50 kg. You see, if you give the same 5 Newton force to this object, you see that the motion wouldn't be the same thing. And this is happening because of their masses. You see that this one has a bigger mass as compared to the smaller one. So just think about it. You lifting something, so a heavy thing, and then something that is not heavy. So they all depends on the masses. So the force that you use to lift the smaller one, if you apply the same force to a heavy one, you may not be able to lift it because of what the size its size is. Okay. So the relativization is just about the body moving or being at rest. So, but we're just saying that it causes the body not to respond to the force that you apply unless the force overcomes the mass. Okay.
So it's like Atia don't go no bolotre in a race.
Come again.
I am saying it's like Atia don't go no bolotre in a
What is
race.
that? Aha. Okay.
A slim body and then
Aha. And then yes, somebody who is heavy. Aha. You can see. You can also compare that. So you see that the slim body should be able to run faster than somebody who
no.
is heavy. So that is also it depends on your mass. So, okay. So any then on the first law. Okay. So don't do that. Okay, so in short, that is all about the first law. The other thing we will be doing is just to apply it when we are dealing with say, problems. Now, the second law, so Newton's second law of motion. Okay, now what does the second law say? Anyone? A trial?
So I'll try.
Okay.
So the second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the mass of the object.
Well, that's a good attempt, but who will polish it up? Yeah, Frank, I think you missed some of the terms, but it's fine. Yes, any other person? Okay. So the second law says that the rate of change of momentum is directly proportional to the applied force, and the body moves in the direction of the applied force. That is the second law. So this states that the rate of change of momentum momentum is oh, is directly proportional to the applied force, and the body moves in the direction of the applied force. Okay. So mathematically, what this is saying is that Now your force F is proportional to change in momentum. Okay. And then we know that momentum is, or momentum of an object is what? The product of the mass and its velocity. So change in P is the same thing as M. Oh, this is rate. So divided by T here. 11 at time rate. So M into V minus U. So this is change of momentum. Final momentum minus initial momentum. Now, if you put this one to our formula, our F will now be equals to, if I introduce my constant of proportionality to be K, I'll have my change in P is M in bracket V minus U, then all divided by time. Now I'll let the constant to be equals to 1. I'll let the constant to be 1. So if the constant is 1, my force will now be equals to M in bracket V minus U on T. Okay. Now, from general physics, when you were dealing with the terms, definition of distance, displacement, velocity, acceleration, and those things, you define acceleration as what? The rate of change of what? Velocity. So A is equals to change in velocity. That's final velocity minus initial velocity divided by time will give you acceleration. So I can say my force is equals to M. Instead of V minus U on T, I will now put my A. So this is the Newton's second law. Okay, the force is directly proportional to the mass multiplied by the acceleration. So this is Newton's second law. And then this is what Frank wanted to say about the statement. He messed up some things. Okay, so that is the law. Now, if you make the M the subject as I initially shown, so you see that the acceleration and then the mass are inversely proportional. These are vector quantities. So you introduce the arrow to show that they are vector quantities. Okay, so that is the second law. Now, when you are stating the second law, this is a condition. The applied force and the body moves in the direction of the applied force. So what it means is that the particle has to move towards the direction at which the force is acting. You only have a bounce back object that will move opposite to the applied force. So for instance, if you hit a ball against a wall, now the ball will first of all move in the direction of which the player is hitting the ball. Then, but because it encounters something, that is why it will be bouncing back. That will now move opposite to the direction at which it was initially moved. But what Newton said is that no matter what the circumstance, when you apply a force to anything, you expect the object to move in alongside with the direction at which the force is acting. Okay, so we can write this one in a differential form. So if I take my force to be equals to d dt on mv. So now I know that mass is constant in everywhere. Mass is a physical quantity that doesn't change with anything. So your mass at anywhere you weigh on this earth will be the same thing. So I can take out the constant term. So I'll have d dt on the velocity, which is varying, with the mass outside. So the mass is not changing. Then I will know that when I differentiate velocity respect to time, it will give me acceleration. So I can basically say that the differential of momentum is equals to force. So anytime you are differentiating momentum, gives you force. So force is the same thing as dp with respect to dt. So you get force if you have momentum. So when you're given momentum and then you want to get force out of the momentum, divide the momentum by time. And when you do that, you get the force. So this is the same thing as ma. The differential of the momentum, the same thing as force, which is the same thing as ma. Now, this force that we are seeing here, since it's external, we say it's what the unbalance, okay, force. Okay, so once the forces are balanced, then acceleration will be zero. So let's say you have a particle that is at rest. So this is a block that is at rest. It's lying on the surface. This block is not moving. So once it's not moving, you expect the net force to be zero. So the force that is acting from this side, the force that is acting to the other side, and this force that is acting down, then the force that is going up, you expect them to be zero. So you say the net force. So the net force, if this is F1, this is F2, this is F3, and then this is F4. So you expect the net force to be the sum of all the forces. So we get F1 plus F2 plus F3 plus F4 should give you zero once you have any object that is at rest. So if you are sitting down quietly, you are not moving. So it means that all the forces that are acting on you sum up to zero. Because once you sit down, your weight is pointed down. There is a normal reaction force that is pointing up to counteract your weight. You are not moving any side. So this force to your right is the same thing as the force to your left. So that will put you at a position that you will be stable. So if you are not stable, you see here you are bent. One side, if one-sided force is greater than the other, then you will be tilted toward that direction. So that's why we are saying that that force is what unbalanced. But if you have everything summing up to zero, it means that you have what a balanced forces. So in that case, it means that if F1, it means F1 is the same thing as F3, F3, then F2 is also equals to F4, so that bounce cancel out. So if this is 2 Newton, so this one will be minus 2 Newton. So when we sum them, 2 plus minus 2 will give you 0. So if this is minus 3 Newton, then this one should be plus 3 Newton. So if you add all these things, so it should give us what? The net force to be 0. So that's what we call the balance force. Aside that, we'll have the unbalanced force. So since we are talking about external force, so the external force is serving as what? An unbalanced force, which will now give the particle an acceleration to move with it. Once the balance force is not 0, then you have an acceleration. So F is measured in Newton. That is the standard unit for measuring the force. Or you can say kilogram per meter, a kilogram meter per second square. So 1 Newton is the same as 1 kilogram per meter square. Okay, so let's know this. Note. So if the vector sum of all the forces acting on the object is 0, then no acceleration, or the object will not move. So then the object will not move. That is into bracket, means that the object will have what? 0 acceleration. Okay. So just as I cited the example. So if you take 2 minus 2 plus 3 minus 3, this will give you 0. So once you're having 0 as your net force, it means that this particle is not moving in any direction. It's just lying down. Okay. So that's the mean. Now, second note is that if the vector sum of all the forces acting on the object is not 0, then the object will accelerate. So 2. If the vector sum of all the forces acting on the object is not 0, then the object will accelerate. Or in other words, you can say the object will have an acceleration. The object will accelerate. Okay. So depending on whichever force that is greater. So let's say I still have this box. Now this is moving. F2 is 3 Newton, and then this is moving in the other side, the opposite side. So F1 is 5 Newton. So it means since F1 is greater than F2, this particle, you expect this particle to move in the direction of what? F1. Okay, so this particle will take 3 Newton, the 5 Newton, the F1 will take 3 Newton to overcome the F2, and then it will use the remaining 2 Newton to move the body. Is that okay? So when you are applying a force to something, now the particle that is moving is not moving with all the forces, because there are other forces that it has to overcome, something like frictional force. That is, if you are dragging in between 2 surfaces, so there must be a friction there. Once the surface is not smooth, there will be a friction. So part of the force we use to overcome that friction, then the remaining one is what the body will now be moving with. Okay, so you expect this particle to have an acceleration in the 5 Newton force direction. So you expect the body to be moved in this side. Okay. You don't expect the body to move towards your left. Okay. So that is what it is saying. Okay. So now we know that mass is the same thing as inertia, and this inertia opposes the motion of the body, or is the reluctance of the body to move. Now we also talk about weight times we misconstrue between mass and then weight. when you are going to the hospital, they say they are taking your weight, and they'll ask you to step on a balance. So one thing you should know about weight is that mass is the quantity of a substance that a body is made up of. That is a mass. The amount of substance present in that thing constitute the mass. But the weight of the object is is it depends on the gravitational field that the body is pulled down with. Okay, so it's a measure of what force of gravity on the object. So that is the difference between the weight and then the object, the mass. Okay. So weight, as we know, when you are determining your weight, it must be your mass times your acceleration due to gravity. That will constitute your weight. Aside that, whatever measurement you are recording on you, if you are not multiplying by gravity, it means that you are recording your mass. Okay. So when we go to the hospital, they ask us to step on the balance. Indirectly, they are measuring our mass, but they always say that they are taking your weight, but it's the mass that you are measuring, unless maybe the instrument is manufactured in such a way that they factor in that Newton gravitational force to get the value of the gene. But some devices, they don't calibrate them with the Newton's meter, so they will just use the grams, and after that they will record it as your weight. So one thing you should also know is that mass is independent of location. So wherever you are, if you record your mass, you go to a different location within the Earth surface, you expect your mass to still be the same thing. But weight will change with change of what? Location. So if you weigh 10 Newton here, you go up to the moon, you don't expect to still have the same 10 Newton, because there's going to be a change in acceleration due to gravity, which will also cause your weight to change. Okay, so let me go through the definition of the weight. So mass of an object is the quantity of substance or amount of substance. Let me use the word amount. The amount of substance the body is made up. But whereas weight of the body is a product of the mass gravity and gravity. So we can say that weight is always mg, where g is acceleration due to gravity. Okay. So weight is also measured in Newton. Measured in Newton. And for that matter, it's a force. So because it's a way you take along the vertical direction, so you have F is equals to mg. Now, when you negate this and put this one here, this will be a unit vector, which is telling us that you are looking at the direction of the force along the vertical direction, which we normally say the z direction. Okay. Now, the negative sign is telling us that the force or the acceleration is always opposite to the direction of the applied force or the movement. Okay. So that is why when you throw any object up, it will definitely come down. The gravity will bring that object to the ground level. So G has a value of 9.8 meter per second square. And this is approximately always written as 10 meter per second square. The actual value is 9, but we approximate it to 10. So in a question, once you are not defined chain, you have the liberty to choose any of them. Okay. Maybe you can use the 10, you can use the 9.8. But most of the time, they will give you the value of change the 9.8 to be used. Okay, so that is Newton's second law. Then we'll move to the third law. We move to the third law. And the third law is the law of action. Third law of motion. Yes, so what do we know about the Newton's third law of motion?
Is it?
Okay.
Is it that action and reaction are opposite and equal?
Okay. So that's fine. So the third law says that in every action, there is an equal and then opposite reaction. Yeah, and all the three laws that he proposed, they are still powerful. And it will not be possible for any scientist to be able to disprove things. Yeah, all the laws that he proposed them at the time there were no technology to verify, but now there are a lot of powerful machines, but yet the laws are still powerful. You check the third law. In every action there is equal and then what opposite reaction, which is true in life. The same thing. You smile because of the feeling that you have. If it's positive feeling, you will smile. If the feeling is bad, you will look sad. So that action will trigger your reaction. See? So if you are being hit hard, yeah, the way the person hits you, the same that the person will feel. You just like imagining a wall. Your mission is you want to use your bare hand to hit a wall. Then you hit the wall by hard, yes, the energy that you exerted or the force that you exerted on the wall, you also perceive it, you also feel it. If you knock it hard, you feel the pain hard. If you knock it small, then the same way you feel the pain. So in every action, there is always equal and what opposite reaction. So that is the third law. If somebody provokes you, you become annoyed. So the action will trigger the outcome. If someone's raising his son. Yes, Mr. Francis. Johan is up.
So with this Newton's third law of motion, which says that actions and reactions are equal and opposite. I want to find out maybe in a school where a class of maybe 40 pupils they
Okay.
misbehave, and as a teacher decided to cane them two each, making 80. Does that mean that the pain that the individuals are going to experience, I'm going to experience times 80 of it, or
Not really. Not really.
I
So
sometimes get confused. If you can elaborate
okay,
on it.
okay. Now the number of stroke that you are issuing depends on how hungry you are. You understand? So if the offense is like too harsh, so you also try to cane them to match up with like the offense. But what the law is saying is that something must trigger something to happen. Okay, so they wouldn't be caned. This is where you started applying the law. You are caning them because they misbehave. So the misbehavior initiated the caning. But as in how many strokes you are going to give to each of them will now depends on the magnitude of their misbehavior. Are you following what I'm saying?
Yes, please.
Okay. So that would depend on them. So you see that somebody can do you something and then you are not like so offended. So you just like, oh, let me not do anything to this person. Let me forget about him or her. So the magnitude will depend on the reaction, like how you react. Okay. So that is the means. The law is just saying that at normal circumstances we shouldn't have like forgiveness. That's what Newton is trying to say. But Jesus Christ is saying that no, we should forgive one another.
Exactly.
Okay, so let's get the law down. So this states that in every action, there is equal and opposite reaction. So what it simply says is that whenever an object let's say object A exerts a force, from object B. Okay, so when object A exerts a force on object B in a direction along the line joining them, it means that object B also exerts the same amount of force on A, but in the opposite direction. In the opposite. Okay, so that is what the law is saying. So if I have the two objects like this, so this is A and this is B. Now A is exerting a force on B. So let's say the force that A is exerting on B is FAB. So Newton is also saying that this one also exert the same force on that. So this will be BA. So the force B will exert on A is BA, and the force A will exert on B is this. So you can see that the force in terms of magnitude will be the same thing. Yeah, in terms of magnitude will be the same thing, but direction will be different. So FAB be equals to negative FBA. So you have this. So that is the third law. Okay, they are having the same force in terms of magnitude, but the direction has changed. Okay. So we should know that the third law normally involves with two objects. So Newton's third law always deal with two different objects. There were two different objects. Always there were two different objects because one must exert a force on the other. But the second law, as we saw earlier, that one depends on or deals with what all the forces that are acting on it. So these are the two different things you should take those from the laws. Okay, so these are the meaning to the three laws, and as physicists, we should know them and then understand them very well because we use them in our day-to-day activities. Okay, so let's look at another important force that since Newton law, third laws Newton's third law. So since Newton's third law involve two objects. So let's say we have what we call friction and then coefficient of friction. A frictional force so since we are not treating the forces into details, if we are to treat the forces into details, we will have the type of forces, which we have contact force and then field force or space force. Now, the contact force, as the name implies, the force that we get from two different things that are in physical contact. But the field force is the force that you experience from a region or a space. So a field force, for instance, you can talk about the gravitational field force. You can talk about magnetic force. You can talk about electrostatic force, or all these things are what field forces. But when you talk about the contact forces, you talk about the frictional force, you talk about upthrust, you talk about thrust, their meaning. Okay, any force that you get as a contact. You can talk about tensional force, all these things are contact forces. Now, one just talk about one of the many contact forces that we have, which is what? The frictional force. And friction is very important in our daily life and then in physics, because without friction, we cannot move on with our everyday activities. Okay, friction helps us in so many ways, in our walking, in doing so many things. Our vehicles, even though because of friction, there's no way that we can drive our vehicles. Any moving object that you've seen on the road is friction that support that. Yeah, we can't apply brakes to bring the moving object to a rest. We can't walk properly, we'll be slipping. Just imagine when there is a water on a smooth surface like a plastered floor. When you slip, how do you feel? So you are trying to reduce the friction if you pour water on a smooth surface. So you see that you slip, the speed at which you will fall. So if there is no friction, right, that is how the movement will have been, and it wouldn't have been possible for us to be moving on. So we want to look at that kind of force. Though it is very useful, but it also have its limitations or some disadvantages, because it also wear out some machine parts like the car tie, our shoes that we wear. When you wear your sandals for some time, you see the soles of the shoes are being worn out. So because of friction. So if there was no friction too, we wouldn't have been facing those challenges. Though it is also good, but it also have its ups and downs. All right. So if you have an object that is placed on a horizontal surface, so let's say this is a surface. I use the white line to separate the two surfaces. Now, I place a block here on this surface. All right, someone's on this up. Yes, Mr. Charles.
Hello, please, there is a feedback. I think one of us, the child is keeping us feedback.
So kindly mute yourself to avoid the echo. Boy, send your phone this way. Send your phone this way. All right, thank you for that. Okay, so now I have this block that is lying down. Now, once the block lies horizontal like this, there is a force we call normal reaction. And this normal reaction is always perpendicular to the surface. So this is the surface. So we have a force which we are calling normal reaction, R. And this is always, okay, so let me say normal reaction. Some books you see N or R. Okay, So either R or N that is being used. And that force is always perpendicular to the surface. So when I say perpendicular means it's form a 90-degree angle with the surface. So that is what we call the normal action. Then there is going to be the weight of that object that will be going down. So this will be the weight. So normally weight is always acting downward. So mg and its mass and gravity. Okay. Now, if your intention is to apply a force to this block to move in this way, so let's give this F as the apply force. Now there's going to be an opposing force to that apply force. So let me give that one as my small f, and this small f is, so let's say apply force and then frictional force. So that you know the differences. So this is apply force, and this will be frictional force. Or friction. Okay, so you can see the arrows. The frictional force opposes the applied force. Okay, your intention is you want to push the line block to your right side. Now, because of the contact between the surfaces, that is the surface of the block and then the ground or where it is lying down, then you feel that opposition. It has to slow your energy down. So we can deduce from what we saw above for balanced object. So for this to have zero acceleration, your apply force, so let me put my capital F here, and then I'll put small f for my frictional force. So you expect your small f to be the same thing as capital F for your body to be at rest. So if it's like that, it means that the body will be at rest. Okay. Then if f is greater than small f, then there's going to be a movement towards the direction of the f. But the normal reaction direction and then the way direction, there won't be any movement. So this is where you have to take note when you are solving a problem of this nature. You only have the acceleration in the direction of the applied force. So you are not looking at acceleration from anywhere where there is no movement. So there won't be any acceleration in the down part or in the vertical part, unless the body is moving vertically up, or the body is being dropped from above and then it's coming down. And when you are using those ones, it means that you need to use your acceleration as what? Gravity. So once you throw anything vertically up, it's going to be accelerated by or impede by what? The acceleration due to gravity. Okay. So we will not be looking at the vertical direction, but the horizontal part, because mostly most of the things that we're doing are moving in the horizontal part. When you're dealing with the vertical motion, it means that you are talking about something you throw vertically up or you drop something above the ground level. Okay, so now what does the friction say? The frictional force, as I said, is a force that opposes the motion of two bodies that are in relative what? Contact. Okay, you can jot that one down somewhere. So, or let's say frictional force is a force that opposes the motion of two bodies that are in relatively contact. So, okay. Now, we normally say the frictional force is directly proportional to the normal reaction. That's one feature of the the frictional force, or one of the features of friction. So the frictional force is proportional to the normal reaction. Okay, so if I say F is proportional to R, okay, now if I introduce my constant of proportionality, this will give me mu R, and mu is what we normally say the coefficient of what? Friction. Mu is the coefficient of friction. So if you look at the formula that the frictional force is proportional to the normal reaction, let me come back here and show you. You see the normal reaction direction. So if the normal reaction, the body is fully lying down on the surface, then it will give you a greater frictional force. But assuming the body is being very small and it doesn't touch the surface wall, then a frictional force will be what? Very small. So that's why we are saying that they are proportional. But one thing you should also know is that the frictional force is independent of the surface of contact. So it doesn't matter whether the body, so you see it as horizontal. So which is here is having a wider area. It doesn't matter when you turn it this way. Okay, so you see that this area is very small. If the contact is small, the frictional force is going to be the same thing. So frictional force is independent of what? Area. Area of contact. Once it is the same material, then whatever frictional force you get when it is lying horizontally is the same thing as when it is lying on the vertical. Okay. So take note of it. Frictional force is independent of what? The area of contact. Area of contact. So, and then 2, it lies between 0 and then the normal reaction. So this is the frictional force lie between 0 and then the mu R. Okay. So you only have it, that is the range it is. You only have it 0 when the surface is completely what? Smooth. So you have frictional force to be 0. Force is 0 when the surface is completely smooth. So in other words, you can reduce friction by oiling your surface, by lubricating it. Okay, so all these are ways of what? Minimizing the frictional force. So aside a smooth bodies, you have a frictional force being this. Now the maximum value it can attain is 1. If the coefficient of friction is 1, that is the highest value you can get. Okay. So you talk about applications of Newton's laws. Yeah.
Sir, please, you say something that the normal value is equals to 1. Can you please repeat it again?
Okay. I was saying that the frictional force has a range, the coefficient of friction rather has a range between 0 and 1. And I'm saying the minimum value, which is 0, you only have 0 if there is no friction. That is, if the surface is smooth. But one thing you should know is that in real life, you cannot just have a surface that is totally smooth like that. That you presume that as the surface is polished or lubricated, it means that there wouldn't be any friction. There will be a 0 friction. Then it can also have a highest value of what? 1. Okay. So when you attain 1, that is the maximum value that you can get for the frictional force. So they at times you see it from 0 to 0.99. So when you're asked to calculate for the coefficient of friction, the maximum value you should get is what? 1. It shouldn't go beyond that. So let me see. I think I will show you that by taking time. So if okay, when we get to like an inclined body, I wouldn't say that one here. When we get to an inclined body, that the body is acted at an angle. Okay, you will see why I'm saying that the maximum value will be 1, because we have to get the angle in terms of tan theta. Okay, when you get a tan theta, the highest value of tan theta is 1. Okay, so I think you will see that one when we are dealing with we'll see it later. Stay. Okay, so I was saying that the applications of Newton's laws, we apply them directly and indirectly. At times we are aware, and at times too, we are not aware or we are unaware. So when you swim in a swimming pool, the swimmer uses the idea of the Newton third law. So you kick your legs on the water, and then as you are pushing the water is also propelling you forward. So somebody that is swimming in a pool is using the Newton's law. The operation of our rockets. So rockets too is also based on the principle of the Newton third law to operate. Okay, that is one of the applications that you can also talk about, because the exhaust gas that is coming out from the rocket exhaust, the fuel that it is being burned, then it ejects this exhaust. Now the exhaust also, as it comes out with a force, it also pushes the rocket to move in the opposite direction. Okay. Okay. So I think when we are solving problem that we will see their applications and appreciate them. Okay. Now I've mentioned about the net force. The net force is the total or is a collective force that a body experiences. So all the forces that are acted upon that body in the various directions, and we put them together, is what we call the net force. So it's more or less the sum of all the individual forces acting on that body. Now, when you sum those forces, you must equate it to the Newton's second law, which is what? Ma. So assuming there is a question that you go like this, maybe the forces that are acting on this particle, and I give you the values. I ask to find the acceleration of the force. Now, if this is F1, F2, F3, F4. Now you say the net force, which is the sum of the forces, must be equals to what? MA. So this will help you get the acceleration that the force. So the estimation of this will give you, you know, when you have more than one thing, you add them together. So your F will now constitute, so F1 plus F2 plus F3 plus F4. This will now give you MA. So once I'm having F1 added to F2 to F3 to F4, then I'll just do the summation sign. So which means that sum all the forces that are acting on the object and equate it to the net force, which is MA. So after that, once you know the mass of the object, assuming this is given as 5 kg, and all these forces are defined to you, and I ask you to find the acceleration that the block will move or the object will move, then after solving for A, then you'll be able to tell which direction that the force will move. Okay, so that's what we call the sum of the forces. Now, when you are having more than one single direction of action, then you have to add the forces based on their direction of action. So you see that F1 and F3 are acting along the X direction. Then F2 and F4 are also along the Y direction. So you have to first of all find the various components of the forces, then you now solve it. Because stretching on these things, because the force may not act directly vertical nor horizontal. Because if you have a force that is acting diagonal to the object like this, now this time around it's not vertical nor horizontal, but it's now diagonal to all the two. So you have an angle, so which you need to resolve this force to the X and Y component before you now sum them individually. Okay. All right. So that is about summing of forces. Because I'm saying this because we are saying that a force is a vector quantity, and you know, vector, we talk about direction. We are not only concerned about the magnitude, but the direction as well. So know these things very well. Okay, so let's now see if we want to resolve a force. Now, in vector resolution or force resolution, you only need to understand the coordinate system. Of forces or vectors. So you understand your coordinate system, which we have the Cartesian plane, we have our positive y, we have our positive x. Now this is for 2 dimensions. Now, if I have a force, a particle in the middle here, and there is a force that is acting to this as F1. Now I have another force that is going this way. Let me give this one as F4. I have one that is going straight to the up. And I'll give this one as F2. Then lastly, I have one which is acting this way. I'll give this one as F3. Now the angle between F2 and F3 is alpha. Now this is the origin. Okay. So you can see that F2 and F1, they are acting vertically up and then horizontally, respectively. So for those one, you can see that F2 has 0 component along the horizontal. And then F1 also have 0 component along the vertical. But for the F3 and F4, they need to be resolved. You have to resolve them to get their X component and then the Y component as well. So this is what we call the X, Y, and then Z coordinate. And Z coordinate. Now you can use the unit vector direction. Last week I think we did that, and I show you what a unit vector is. So when you have the ij, so you also sketch this in the 3 dimensions. So this is our k. This is, you can put here I or j, it doesn't matter, whichever way you want to go. And this is our I. Now these are also the unit vector. So when you have this, you try as much as possible to resolve your vectors according to the given coordinate system that you are working with. So let's say we want to find the net force for the F1 to 4. So finding the net force, so we can say that the net force so let's say resolving the forces into their components. To their components along the X and Y. And Y axis. We have the resultant force as this. So summation of the forces gives you F1 plus F2 plus F3 plus F4. Everything should give you 0. That is, if there is no movement. Okay, so come back here. You see, I equated everything to MA. And I stress that if we have found the acceleration, it means there is movement. But once the forces are acting on the object and the object is still at equilibrium, it means that there is no acceleration. So you equate it to 0. So that's what we are doing here. So we are presuming that the forces that are acting on this circle in the middle here is not moving. So you sum all of them and equate it to 0. So how do you sum it? You sum it according to the component. So the summation of the forces will give us F1 in the X direction, then F1 in the Y direction, plus F2 in the X direction, then F2 in the Y direction, plus F3 in the X component, F3 in the Y component, plus F4 in the X, then F4 in the Y. Everything to be 0. So you can also write your 0 as in a vector form like 0, 0. So it means you add the upper part, that is the X components, equated to 0. Also add the Y components equated to 0. Okay, so if you want to resolve the first force, let's go back to the diagram. See that the first force is acting along the X. So look at our X component, X. Now, let me take you back small for a right angle triangle. So when you are taking a right angle triangle, you use your 3 ratios. So let's say you have something like this. Now this is a right angle triangle. So you're going to use your SOHCAHTOA. Okay. So the other time I show you where the angle is facing is always your opposite side. So this will be my opposite side. And then the side that the angle is lying on is my adjacent. So this will be my adjacent. Then obviously the longer side will be your hypotenuse. Okay. Now use your three ratios. SOHCAHTOA. Okay. So sine theta goes with opposite over hypotenuse. So O over H. That's what we say. So then cos theta is adjacent over the hypotenuse. Then tan theta will be opposite over what? Adjacent. So that will be your tan theta. So tan theta be equals to opposite over adjacent. Okay. So now we are going to use these ones to now resolve this F1. So let's say here that I'm using my hypotenuse. So if I want to get any other side, since I have my hypotenuse, if I want to get my opposite side, I will use sine, and then I'll get H sine theta will give me my opposite side. But H cos theta will give me my adjacent side for this one. Okay, that's how you will do it here. So let's come here. We see from here that the angle, the force is acting on this line. The F1 in this case is acting like this. It's acting directly on this line, which means that, like you see, initially, let me clean this and then say something before how it has erased. So you see that I have this white line, and then this is what I show you: theta, opposite, adjacent, and hypotenuse. So let's say if I now bring this red line that you are seeing here to lie on exactly this white line here. So if I do that, so this is, so assuming like this one was my F1. So now I'm bringing my F1 down here. So you can see that once I've brought F1 to lie on the X coordinate, this theta will not be here. So let's say I've now removed this. So I've removed this one to lie on it like this. So there is no theta again. So the angle between it will be what? 0. So you come and then resolve it this way. So you take the force that is there, the upper part takes cos, that's the X coordinate, take cos, then the down, the Y coordinate will take sine. So this one will now give me F1. Then since I'm dealing with the X coordinate, I will take cos. But the angle, as I shown, will be 0 because there wouldn't be any angle between there is no angle between this red line and then the white line, that's the direction. So the angle is 0. So I have 0 cos 0. That will give me my X component. Then this one will give me F1, then sine 0. So I'm done for the first part. Then plus, I'll come to the second force, that's F2. Let's see, F2 is facing where? Directly vertically up. So the same way, because if I also here, so my red line was here. Okay, so if I also decide to take this red line and let it align with the vertical, still this angle from this side to this side will be 90. Okay, from the white line to this one will be 90. So it means that the angle becomes 90 degrees. So let's come and apply that. So for the second force, which is F2, I'll have my F1 to give me the S coordinate to be F2, then cos 90. That's now the angle. And this will be F2 sine 90. Okay. Then F3. You look at the direction at which F3 is facing. Let's go here and see F3. The direction is F3 facing. So F3 is facing here with an angle of alpha. So we'll still use that, but there is some small thing that we need to do it. So this one will still be cos. So this is the angle. Now this is going to change. Look at it here. If I close this up here, assuming I close this one up, this is now my 90-degree angle. So the opposite side will now be my x. I don't know whether you're seeing it. Let me sketch it somewhere so that you can see what I am saying. So let's say I want to redraw only the F3. So I have my X and my Y coordinate like this, but F3 is acting this way. So this is my F3 here. Now this is my alpha angle. So if I close this one with this, so you see that I have a right angle triangle here. So now I'm going to still apply the side that is facing the angle is my opposite side. So this side now become opposite here, not like the first one. See, the first one, the opposite was vertical. But this time around, opposite becomes what? Horizontal, depending on the location of the object, the angle. Then here will be my adjacent. Now, I can still use a cos and sine for this. I have to change because this time, assuming I want to find this side. This is x and this is y. Assuming I want to find x and y. So let me find x value. So x value, we are still using this SOHCAHTOA one. I want to find my x now become opposite. That's O. So O, I will use sine. You see it. Sine is having the O here. So it means I'm going to have sine alpha. Sine alpha will be equals to x, which is opposite, over my F3. Okay. Then F3, if I make x the subject, it means that my F3, x will be equals to. So if I do that, my x now becomes F3 sine alpha. You see that now the x component is taking sine, unlike the first one, the previous one that the x component is taking cos. If you look at it, the F1 is taking cos, F2 is also taking cos. But because this angle is now with reference to the vertical, then you have to change the sign. You can't still go by the cos. Okay. So if I also look for y, so y here will be what? Cos. Y become my adjacent. So adjacent side will be a cos. So it means that y will be equals to F3 cos theta. But you ask yourself, look at the coordinate or the location that F3 is. So when you draw your Cartesian plane like this, here is positive, here is positive, here is positive, here is negative, here is what? Negative. So negative y, negative x, positive y, positive x. So when you are in this coordinate, you are within the x coordinate of the negative coordinate of x and the positive coordinate of y. So it means that whatever value you have for x for this must be negated. So it means my x value must be negative here. Okay, so you go and write this one there. That would be F3 minus F3 sine theta and then F3 cos theta for this. So when we come here, so plus our F3 here will now be minus F3 sine theta and sine alpha, sorry. And then this will be F3 cos alpha. This is how you resolve it. Then the fourth one, let's also look at the direction of the fourth one. So the direction of the fourth one is also like this. So that one too is like this. Is found in this quadrant. So this is our F4. So you can't, let me see, where is there a dark angle? Yes, there is an angle beta. Oh, sorry, I didn't bring the beta. So the angle is here, beta here. Okay, so let me use this one to also explain. So here is beta. So beta here. So if you close this to make a right angle triangle. So, okay, let me make it this way. So I'm making a right angle triangle here. The same way, here will be my opposite side. So let me say, but this side is what? X. and this is my adjacent y. So you use your SOHCAHTOA to get x will be sine beta will be equals to opposite, which is x over f4. So which means that x is equals to what? f4 sine beta. Okay, then to get your y, that's going to be cos beta be equals to adjacent, that is y over f4, which means that my y is equals to f4 cos beta. Now, you ask yourself in the location. So here is positive, positive, negative, negative. So here you are in the range of what? Negative x values and then negative y values. So it means that whatever you get here must be negated. So this will be negative. This is negative. Then you come and then add it to this one. So plus. So plus, you write your x value. The x value is minus f4 sine beta. So this is minus f4 sine beta. And this will be minus f4 cos beta. Okay, so that is how you resolve. And this will be our net force. So everything here is equals to 0. Then you add. So now, if you know the value of f1, so you take f1 cos 0. And you know that cos 0 is 1. So obviously, you'll be left with f1, and this one will go to 0. So if you go down further, this side will be 0 because sine 0 is 0. When you come to the second one, cos 90 is 0. So this will be 0, and then there will be a value here. So here you have value for all of them, but this will be negative, and this one will be positive. When it comes to the fourth one, you have values for all of them, but they will all be negative, negative. So this is how you resolve a force or a vector that is acting diagonal or let me say diagonal or directly, vertically or horizontal. So there's no the coordinate system. Then the three ratios, the sine, cos, tan, if you know them, then you apply the sine depending on the location. Okay? Depending on the location, whether it is in the first quadrant, second quadrant, third quadrant, or fourth quadrant. So you assign the sign to them. Yes, any question, please? Any question? If you see something like that, can you be able to do? Yes, Mr. Samuel.
Sir, please, can you please go over the F2 for me?
Okay. The F2. So let me take you to the diagram first. So look at where the F2 is pointing vertically. So I'll come here and then show it to you. So this is your Cartesian plane drawn. X plus y plus y negative. X negative, y negative. X negative, y negative. Now, I'm now letting my force apply on this. So this will be the direction of my force. F2. So the F2 is lying exactly on the y-coordinate. So the angles are measured from positive x counterclockwise or anti-clockwise. So you start the measurement from positive x, this direction. So this is the direction at which you measure the angle. So starting from the positive x. So this is a 90-degree angle. Okay, so it means that the angle between my F2 and then the positive x axis is 90 degrees. Now, if you want to resolve this, the x coordinate, look at it. If the angle is sitting on the x coordinate, that's the x, the horizontal line. So the thing is measured this way. This. So So this is theta. You see that this angle is making reference to the x because this is x. So once the angle is in between the line and then the x coordinate will take cos, and then the y coordinate takes sine. You understand? Now, when I move this blue line to be this one, f2. So it's f2x and then f2y. And then f2x is equals to f2 cos 90. And then f2y is also f2 sine 90. So you now resolve it. And assuming the magnitude of f2 is known, maybe if it is 10 Newton. So you now have 10 cos 90, and cos 90 is 0, which will give you 0, and which is true. If you have a number, like a value that you have 0 and then 1, which means how do you plot this? So if you want to plot this one on the Cartesian plane, you come the origin, then you move to what? 1 unit along the y. So you have it this way. So which tells you that you have 0 on the horizontal, but the value is there at the y. So you will join your line like this. Okay. So you see that you have 0x and then 1y, or any number of the y. The same way, if you also have 0 on the y and you have a number on the x, then you should be plotting along the horizontal line. Okay. So that is how you will do for the f2. So don't confuse yourself with the location of the angle. The first one, the scenario that I'm making here, this scenario is that if the angle is in between the line and then the horizontal line, you are using cos for the x, you're using sine for the y. But when you have it this way, and the angle is now located in between the vertical and then the line, you can also use the cos for the x and then the sine for the y. You have to also swap them. So once the angle is in between here, we are going to use sine for x, and then you use cos for y. Okay, and this one is that just coming out of the blue. So that's why I say you have to use the SOCAT one. So if you have it this way, now this is your angle. The side that is facing the angle is what? Your opposite side. And this is a horizontal line. Look at it. This line is horizontal. And horizontal lines are normally represented by what? X. So this will be X. Then this vertical line is your Y. Now, when you use the SOCAT one, so is opposite. So opposite means X, because this is the side that is facing the angle. So you see that X will now be, sine theta will now be equals to what? X over whatever you have. Okay. When you're able to identify the location of the angle, now the next thing is you look at the coordinate, the quadrant that it is found. Is the angle found within the first quadrant? If it is within the first quadrant, yes, like this. So this is 1, 2, 3, and then 4. Because I said we are measuring like anti-clockwise. You don't go 1, 2, 3, 4. You move in the other way. So if it is in the first quadrant, all of them are positive. So X, positive X. Here you have positive X, you have positive Y. Then when you are around the second quadrant, so this will be minus X and then positive Y. When you are in the third quadrant, you have negative X, you have negative Y. Then when you are in the fourth quadrant, you have positive X and then negative Y. So those signs that I was indicating is coming from the sign convention here. So you look at the quadrant that you are. In that quadrant, am I dealing with all positive values for the x and y? Am I dealing with all negative, or one is positive, the other one is negative? Then you apply that sign. That's it. The calculator is designed in such a way that it understands certain things. So the calculator understands acute angles. When you take sine, tan, cos of any acute angle, that is 0 to 90, it will automatically give you a positive answer. But that is how it has been designed. So it understands that you are dealing with the first quadrant. So when you take your calculator, you can type any angle that is within 0 to 90 using sine, cos, and then tan. It will give you a positive answer. But some people are there, they can find an acute angle within the second quadrant, for instance. So let's say I'm giving like 120-degree angle. So which I want to measure 120. So I know that 120 will definitely be in this quadrant. So 120 like this. So from here to the x, this angle is 120 degrees. So somebody can decide to do it this way because the person knows that this angle alone is 90 degrees. The person can say, okay, since I know this is 90 degrees, this one is 90 degrees, so I'll put 30 here. You see it, and you want to use this 30 to work. So if you type this 30 in your calculator, the calculator will understand that, oh, you are looking at this quadrant. I mean, while you are in the second quadrant, so it will give you a positive answer. So it can't think like you as a human being. So for you to differentiate between whatever you are doing, you have to now say, okay, where I'm looking for the 30 is having a negative x. So you will now write the negative for the answer that the calculator will give you. Okay. But if you just type the cos of 120 and then sine of 120, the calculator will give you a negative answer of the x and then give you a positive answer to the y. So you understand that. Okay. So somebody can decide to also use this one. And at the end of it all, you get the same thing. Somebody can also, okay, the whole of this one is also 90. If I know that this is 30, so this is 60. The person can also work with this 60. So another person, so this is how you can write it. So this one will be cos 90, cos 120, it's the same thing as negative sine 30, which is the same thing as minus cos 60. So if you want, type these things and see. Pick your calculator and type 120, cos 120. The answer you will get. Type sine 30. The answer you will get, it will be the same thing, but you have to now attach the negative sign. Then come and type cos 60. You get the same answer, but you have to now indicate, because this one obviously will give you a negative answer. When you type cos 120, it will give you a negative answer. When you type sine 30, it will give you a positive answer. You type cos 60, it will give you a positive answer, but the same value. But you have to now put the negative sign because of what you are using. Is that okay? Are we together?
Yes, sir.
Okay. Yeah. Lucky. Understand.
Yeah, yes, sir. So I want to find the last, this is the F4. Is it the first one, is it negative? Cause,
yeah, they are all negatives. Sorry, because I'm working today. The latter part, the tip part of the slide as well. So all of them are negatives. So let me see if I can use a different color. Should write there. So they're all negative. Okay. Can we continue? So as I was saying, if you proceed that by putting the angle, so f1 cos 0 will give us f1. Then f1 sine 90 will be 0. So the first part will be f1 0. The second part will be the top one, cos 90 is 0. So that will be 0. Then we have f2 sine 90. So sine 90 is also 1. So we have 0 f2. Then when we come to this, since we don't have we've not defined f3 and then alpha, then we still have the same thing. Then this one too, we still have the same thing. And we equate everything to 0. So assuming we define our f3 and then alpha, f4 and then beta, then we will get a number for the x coordinates. We equate to 0. So we also have that for that one. And since it's the force is being equated to 0, it means that the object is at equilibrium. So at the end of it all, we should get everything sum up to 0. So when you add them together, you get 0. You add the f1 to the 0 to the minus f3 sine alpha plus the minus f4 sine beta. It should give you 0. And you also add it down, it should be 0. You only have being equated to ma if the particle is moving. Okay. So that's why you can solve for the acceleration if the mass of the particle is provided. Okay, so I do that, you get it two equations. You got equation in terms of the vertical, then in terms of the horizontal. Then you solve it simultaneously to get whatever you have to do. All right, so let's try an example. So example. Now, find the magnitude of acceleration produced when a particle of mass 4 kg is acted upon by a resultant force. This is just like, okay, say, let me write this. Okay, no problem. We teach from the new book. So let's start with the easiest one. Find the magnitude of the acceleration. Of the acceleration produced find a particle of mass. Particle of mass. When a particle of mass 4 kg is acted upon by a resultant force of magnitude. Force of magnitude 16 Newton. Okay. So solution. This one there is easy, but let's whet our appetite with the easy question. So we'll move ahead. It'll be better than if you start with something that is complicated. So now you start by stating your formula. F is equals to ma. Now F is giving us 16 Newton. Mass is giving us 4 kg. And what is the acceleration that is going to be produced? So you substitute your formula. So you have 16 equals to 4a. Then you make a the subject. So it means that the acceleration produced will be equals to 4 meters per second squared. So that will be the acceleration you are going to obtain if you apply a 16 Newton force to an object that has a mass of 4 kilograms. All right, so that is one there is okay, right? Now let's look at another one. 2. Find in vector form the acceleration in vector form let them work on your sonus for you. So find in vector form the acceleration.
Two CDs. Mama. Yeah.
So you call that person to come and read for. So sorry for that, please. Find a vector form of a particle of mass 600 kg. Grams, 600 grams. When forces of 7I plus 3J Newton, then 4I plus 4J Newton, and minus 2I minus 5J minus 5J Newton act on it. Find also the magnitude and direction of the acceleration. Find also the magnitude and direction of the acceleration. Okay, so the same way we extract our data. So we have 3 forces being provided, and the choice is to get the vector form of the acceleration. After that, we use that one to find the magnitude and direction of it. Okay, so let's get our data. We have the mass to be equals to 600 grams. So since force is in Newton, we can't use a gram. We have to convert it to a kilogram. And in every 1 gram, we have in every 1 kilogram we have 1,000 grams. So by conversion, this would be 0.6 kilograms. Then our forces are there. So since the forces are acted upon in 2 directions, that's I and then J, so in other words X, Y, we have to add them. So we'll add our net force, so F is equals to MA. So it means that we need to get the net force. So we add them together equal to this. Now we'll have our A to be equals to the sum of the forces divided by the mass. Now let's add our forces together. We have 7I plus 3J plus we have 4i plus 4j plus we have minus 2i minus 5j. Then all these divided by, you can stop, divided by 0.6. Now we are summing them vectorial because it's a vector sum. So at the end of it all, your answer should still be in a vector form. So you add the i's together, add the j's together. So we're going to add 7 plus 4 minus 2, and that will give us 9. 7 plus 4 is 11, minus 2 is 9. So if that's our A is equals to 7i, then we also add the j's together. We have 3 plus 4, which is 7, minus 5. So 7 minus 5 gives us 2, positive 2. So that will be plus 2j. Then this is still in the vector form, then it's been divided by 0.6.
The I was supposed to be 9.
Oh, sorry, it's 9. Thank you.
Yeah, thank you.
It's 9. So this is 0.6. Now you can leave your answer like this, or you divide each of them by 0.6 if you want. So this would be meter per second square. So this would be your acceleration. Or you can choose to divide 0.9 by 0.6 and then 2 by 0.6. So whatever you get, you write it. Now that's the first part of the question. And the question says also find the magnitude and then the direction. So now to find the magnitude is to get the acceleration value. So that will be equals to the magnitude. We saw it last week. So you take the 9 square or the 9i square if you want, plus 2j square. But we have to add this. Let's simplify this one first. Divide 9 by 0.6 so that we write it down and use that one. Or if you don't want it that way, just divide each of them by that. So here will be 0.6 everything. Or let's make it simple. So just divide 9 by 0.6. Those we can.
That one is 15.
To give us 15. Sure.
9 divided by 6.
9 by 0.6 is giving us 15.
Okay, so
It
15
will give you 15.
I.
What
about 2 divided by 0?
I want to 3.33. 3.33.
Okay, 3.3.
It's a recurring.
Okay, 0.33. All right, that's fine. Okay, so this is what you have. Then you come and then use this one to find the magnitude. So, and shall just forget about the direction because we know that I dot I is equals to 1. So you just pick the numbers. So the magnitude. So 15 square plus 3.3 square. 3.33 square. Okay. Then find the square root of it.
15.365.
Okay.
We are
So
getting
15.36.335, right? 65, so you can make it 37. So you can make it 37. Okay. 365, so you just make it 37 to 2 decimal places per second square. So that is the magnitude. Now the direction is, so you put this one in the Cartesian plane like this. The direction is the angle. So assuming we are plotting this, so we have 15 along the x, so your 15 is here. Then we have 3.33 along the y. So this is my y. So let's say my 3.33 is somewhere here. So they are all positive. So I'll have it, if I intersect this, they will meet somewhere here. So I will join this line to the origin. So once you join this, so this is what you are asked to find. That's the direction. So I know opposite side because this side is 3.33. Then the adjacent side is 15. So I will use my tan. So tan theta is equals to our opposite, which is 3.33 divided by adjacent, which is 15. So this implies that theta is going to be tan inverse of 3.33 on 15. So find the angle. Whatever you get will be the direction. All right. So this is going to be 12.5 degrees. So the direction is going to be 12.5 degrees, or you can say 12.5 west of north, or west, west of north or northwest. So that is how you find the direction and all that. Yes, any other thing? Any question, please? Do we understand? If you get something like that, can you do it?
Yes, sir. We understand this one.
Okay. Right, so one more example, and we'll move to a new thing. So example 3. Now, due to a force field, a particle of mass 5G, due to force field, a particle of mass 5G moves 5G moves along a space curve. Along a space curve whose position vector is given as a function of time by r is equals to 2t keep plus ti plus ti, then plus 3t to the power 4 minus t squared plus 8j, then minus 12t squared k. Okay. Find A. the velocity. Then B, acceleration. Then C, the force field at any time t. Okay, at any time t. All right, so solution, get our data down. Now you are given the mass to be 5 grams. As usual, you change it to kilogram. And this will give 0.005 kg. Now our position vector is giving us 2t keep plus t all in the I direction plus 3t to the power 4 minus t squared, then plus 8. That is on the j direction, then minus 12t squared k. Okay, so that's our position vector. Now we are asked to find the velocity. So velocity, as we know, is the differential of the displacement with respect to what? Time. Or in short, velocity is equal to what? Distance over time. So you get that. So now you're having the distance, then you need to differentiate this one to get the velocity. So you differentiate the position vector respect to time. So you start by differentiating 2t keep. So when you differentiate 2t keep, you get 6t squared. Plus you differentiate t, you get 1. Then you bring the direction, which is I. Plus we differentiate 3t to the power 4. That will give us 12t to the power 3. Minus you differentiate t squared, you get 2t. Then if you differentiate 8, 8 is a constant, it gives you 0. So the direction is j. Then minus, you differentiate 12t squared respect to t will give us minus 24. Then t. This is along the k direction. So that's for our velocity. Now the second part, B, is saying that the acceleration. Now before you get acceleration, you have to have velocity. Once you move from distance to velocity, then you can move to what? Acceleration. So acceleration also equals to what? Velocity over time, which is the same to the v on the t. So now we've gotten our velocity to be, or the r square on the t. So we differentiate this one again. So we are going to differentiate it the second time. So that will give us 12t. Then this one time is 1. So a differentiate 1 is a constant 0. So we are level I. Then plus differentiate 12t keep, give us 36t to the power 2. Minus you differentiate 12t, that gives us 2. Then this will be along the j direction. Now we have 24t. We differentiate that one will give us 24 along the k. So this will be our acceleration. Now the C part is saying that the force field at any time t. So C is talking about the force. So force is equals to ma at any time t. So now we have our A, we have our mass, so we can get a force. So that's going to be 0.005 multiplied by the accelerations, which will be 12t I plus 36t squared minus 2j, then minus 24k, then everything. So that will be your force. Then you bring the unit Newton. So you can expand by multiply through by the mass. Now the anytime t is because you will still have t in the first expression because of t wasn't defined as a number. So that's why the question is saying that in any time t. So that will be the first row in any time of the t, the time. Is that okay? Are we together?
Yes, sir.
Or we are tired?
No.
Are we tired?
No, sir.
We are following.
Okay.
Please, the question. Are you going to open
Yeah.
the
Your line is breaking up, please. I can't hear you. The one that said the question, your line was breaking.
Yeah,
I couldn't hear anything.
Oh, sorry, sir. The force, will you use the 0.005 to multiply what is in the bracket there, or you leave it the way it is? I'm talking about the C.
Oh, you expand. Expand by multiply through by the 0.05. But if you leave it like this, there's nothing wrong with it. But for the purpose of the marking scheme, you have to go further. So times, if they are giving it to somebody who is a physics bias to mark, the person will understand. But if they give it to somebody that doesn't understand what you've done, once the person sees what you've written and it doesn't matches with the marking scheme provided, the person will be attempted to mark you wrong. So it'll be advisable you simplify to the simplest form. Is that okay?
Okay, sir.
Hello, sir.
Yeah.
My line broke. When I came, you guys have started solving it. Please say.
So
I want to see the question. Did the question say we should differentiate? Because I've seen some differentiation here all over.
Yeah, the question is saying you should find velocity, you find acceleration, and then force felt. So
okay,
once you are given a distance and you want to get a velocity out of distance, how do we define velocity? We say velocity is what? The rate of change of displacement. That is velocity. This speed is what? The rate of change of distance. So once you are having a position vector is about your location, your position, that is your distance or your displacement. So if you want to get velocity from the position, you divide it by time. And divided by time is what we've taken it as what? A differential. So it's like finding the gradient of something. So when you want to find the gradient, you plot a graph and you find the gradient, you take the increment in the vertical divided by the increment in the horizontal. So that small change is what we change into the differentiation. So you differentiate with respect to time to give you velocity. Now, when you also get the velocity, how do you define acceleration? Acceleration is what? The rate of change of what? Velocity. So once you also have velocity, divide the velocity by time, you also do acceleration. So you have to differentiate the position twice. In other words, you have to differentiate the velocity that you found. Then when you differentiate the velocity, that will give you acceleration. Now, you are looking for a force. And force is what? Mass times what? Acceleration. So once you have acceleration and you have the mass, then you can tell the force. And your force will still have the t terms because the question said you should find the force field in any time of t. So t wasn't defined. If they say for time t is equals to 2, then you now go into the force expression, then substitute 2 in place of the t, and that will now give you a number without the t values. Is that okay?
Okay, sir. Thank you, sir.
You're welcome. Okay, so when are we supposed to go for our break? The break time is what time? Or we should continue?
Yes, I think we should continue.
Okay.
I don't know for the others.
We'll
The
continue.
break time has elapsed. We're supposed to be 1:50 to 2 o'clock.
Let's continue.
All right, that's okay. Let's back some. So let me give you another example, and then after this we move to Newton. So you try from no examples and then solve. Okay, so this is 0 under the equilibrium of 4 forces F1, F2, 4 forces F1, F2, 10 and 18. Find the magnitude of the force F1 and F2. Okay. So I think this should be our fourth example also. The figure below shows an object placed at 0 under equilibrium under the equilibrium of 4 forces. Of 4 forces. Of 4 forces. We have F1, F2, 10 Newton, and 8 Newton. Find the magnitude of the forces. Find the magnitude of the forces F1 and F2. Okay, so this is the figure. So we have the figure like this. So this is 10 Newton. Here is 6. Here is 60. Then here is 30. That's F2. 30 here, 30 degrees. Then we have F1 here. Okay. And this is 8. 8 Newton. So we have the X and then the Y. Now there's a figure, and we want to find the values for F1 and then F2. Now these are the information given. Now let's come to our solution. So just as we saw from that one, we have to resolve these 4 forces to the X and Y values, then equate everything to 0. So the sum of the forces is equals to what? 0. So it means that this will be our F1 cos theta, F1 sin theta. Okay, let me not just go the formula. Let's do it together. Let me solve with you so you understand. From putting it, you may get confused. So this one will be F1 plus F2 plus 10 plus 8 be equals to 0. So let's first of all get the resolution. So you come to diagram, you see the 10 Newton force is acting horizontally, and that means once it's acting along the X direction, there is no angle between it. So we can have our X1 component to be like this. So my F1 is equals to F1 cos 0, F1 sin 0. And this is the same thing as 10 cos F. Oh. All right, so let me make it this way. So let's say F1, F2. Let me give this one F3 to be equals to 8. And then this one should be F4 to be equals to this. So I'm talking about F4 because we have F1 here. So F4. So let me say, where is my F1? F1 is here. F2 is here. Okay, no problem. So then let me do this. So here will be 30, but the whole of this is 90. So let me put 30 here for this angle. Because when you take 60 out of 90, you are left with 30. So my F1 here will be this. So this time around, this is not 0 because I've kept 30 here. So 30 here, but because I have changed the position, this time around, the angle is now between the vertical and then the line. So I'm not going to use cos for the X and then sine for the Y. Unlike this, this one, the angle is 60 is within the horizontal and then the line. So that's why I will use the cos and then the sine. So this time I have to switch it. So this one will give me, so this one should rather take the sine. Sine 30, and this one will take the cos 30. I hope everybody understands what I'm saying. Because if you don't understand the other part, now that we are using an example to solve, this is where you should get it. So in short, what I'm using here is that, so let me take this one alone. Just pick this one out. I have something like this. So this would be my right angle triangle. This would be my 30 degrees. Now this is where my F1 is. So I have this side to be 8. Oh, I'm making something wrong. I'm making something wrong. So this is like this. Let me take out this. This is not there. I'm making an error here. So this is like this. So this is my X, this is my Y. So the F1 is on this. So this angle is 90. So this is right. So let's look good here. I was making a mistake here because of this. So this will still be cos and then sine, but it will now be 90. So this will be cos 90. This will be sine 90. That's for the F1. Okay. So the F1 is just like what I've said here alone. So now when you come to F2, so F2 is like this. So my F2 will come this way. So F2 is down here. It's down here. So I'm looking at it this way. Now this angle is 30 from here. Now this side is my F2. So you see that down here is horizontal, that's X, and that is opposite. So this is where I will switch. So here I will take sine. So if I put here Y, and then this side X. So I will look for X and Y. So it means that sine theta is equal to opposite, which is X, over the hypotenuse, which is F2. So which means that my F2 will be equals to, my X will be equals to F2 sine theta. So X is equals to F2 sine theta, sine 30. And then my Y obviously will be F2 cos 30. Then you ask yourself, which quadrant is the angle? There is in the third angle, and that this one will be negative, this one will also be negative. So it means you have to negate all of them. So negative, negative. Okay, so let me come and write that one. My F2. Yes. Go ahead,
Sir, please, I have a question. Sir, please, can you please go back for me?
Sorry.
My question is this: the 30 about the F2, the 30 degrees, is it between the F2 and then the negative Y axis, or the F2 and the negative X axis?
Okay, it's between the negative X and then the Y. Let me see, because if I put this straight line here, so if this is my Y and this is my X, so it'll be between, then I've interchanged it here. It'll be between the X and then negative X and then the line. Okay, so here I'm using this. So what I've done here wouldn't be anything. So I have to just change this. If I want to go by what I have done, so this one would have been 60. And that is the same thing. Because if this is 30, if here is 30, so here will be 60. So it means that my angles here are 60, not 30. So thank you for the correction. So there will be 60. Please, are you following what we are doing? So if you want to go by the 30, it means you will not switch. You will still go by the cos up here, then the sine down here, because the 30 is between the line and then the X. So if you are going by 30, so it will still be F2 minus F2 cos 30, then minus F2 sine 30. But if you are going by 60 like what I've done here, then you must switch it. Because assuming we are going by the 30, look at where the 30 is. So in other words, we will have been looking for this side. So this side would have been our y, and this side would have been our x. So when you take a sine, this side will be your opposite. So you see that the y will be opposite, but the x will still be the adjacent. So in that case, it would have been, what I've written here is the same thing as minus cos 30, then minus sine 30. If you press on your calculator, you see that it will give you the same answers. If you want, take your calculator and press sine 60, the answer you will get will be the same thing as what? Cos 30. But we are just putting the negative sign in all of them. So if you do it, you get the same thing. Okay, so we'll come and write it here for our F2. So our F2 will be equals to minus F1. So everyone will still go by the cos 30, you understand that way, or the sine 60, they're all the same thing. So cos 30, and then this will be minus F2 sine 30. Okay, so this one can also still be simplified. So F1 cos 90 is 0. So this one will be for 0, and then this will be F1. So F1. Then press somebody should check cos 30 for us.
Root 3 on 2.
Okay, so this one will be minus root 3 on 2. What about sine 30? Half.
Yes, half.
Yes, please.
Okay. So minus half. So this is what we have. Then let's go for the third force. Now, the third force is the 8 Newton. So that one means we are measuring the angle from this, from the x to this. So that is your angle. So that can still go by that. So when you use your x and y, you take the cos. So that one, it means that the x coordinate will be equals to, now you have 8. So you will use sine. When you use sine will be opposite. That will be the y, and then the x will be the adjacent. So cos, this will be cos 8 cos 60, and then the y will be 8 sine 60, because you're going to use a SOHCAHTOA. So sine theta, sine 30, sorry, sine 60 will be equals to the opposite side. Sine will take opposite. So the opposite side is going to be here. So this is parallel to the y. So this side will be your opposite side. So that will be y. So y over 8. So when you make y the subject, you have what? 8 sine 60. Then the cos the 60 will be equal to adjacent. So that will be x over the 8. So when you also make x the subject, so you have this. So that will be the coordinate for the third force. So the third force will have F3 to be equals to, we have 8 cos 60 and then 8 sine 60. And because of its location, you don't have to add any sign. When you press your calculator, you see it. So this will just be positive because it's an acute angle. So you have that. Then you're saying that cos 60 will be half. So that will be 4. Because half times 8 will be 4. Then sine 60 will be root 3 on 2. So root 3 on 2 divided by, that will be 4 root 3. Is that right? So 4 root 3. Okay, so now we are left with the fourth one. So let's do the fourth one here. So F4. We're given F4. What is the F4 direction? So F4 is pointing on the horizontal. So is that like the F1. So that one will have 0 angle there. There's no angle between the x-axis and then F4. So that one will be, so our F4 is going to be 10 cos 0 and then 10 sine 0. So cos 0 is 1, that will be 10. Then sine 0 is what? 0, that will be 0. So now these are our forces, F1, F2, and F3. We'll substitute everything to this equation. So you substitute the value for F1, which is 0 F1. Substitute the value for F2 minus this and that. Substitute the value for this to that and then this. Then you now solve for it. So let's go. So our F1, 0 F1. This will be 0 F1 plus. Then we'll have minus root 3 on 2 and half. So minus root 3 on 2 and a minus half plus 4 and then 4 root 3. 4 and then 4 root 3. Then plus 10 and then 0. Everything is equals to 0. So you pick the first one. Our F2 is missing. Where's our F2? F2 is missing somewhere.
F2 is there.
Yeah, so here we have F2 here. Because I only wrote the sign value, but I didn't multiply by the F2. This is F1. Because it's F1 times cos 30. So here will be F1. Multiplied by F1. Here will be multiplied by F2. Are you following? For the second force, it should be multiplied by F1 and F2. So here will be F1. So here will be F2. Okay, so let's pick the top one first and solve for F1. Also pick the F1. Come on, I misplaced this. Okay, F2. Yeah, F2, F1, F2 is correct. So the position is right. Okay, so we are taking 0 minus 0 minus root 3 on 2 F1 plus 4 plus 10 to be equals to 0. So we have root 3 on 2 F1 to be equals to 14. So that is by taking this one to the other side of the equal sign. So that will be 14. Then we make F1 the subject. So F1 will be equals to 28. That's 14 times 2. We multiply it by 2. Here by 2. So 28 over root 3. Okay, so you can simplify it. Then you pick the down one. We have F1. So somebody should simplify this one and let's get the answer. So also the F2, where's the F2, the down part? So we have F1 plus minus half F2 So F1 minus half F2 F2 then plus 4 root 3 plus 4 root 3 then 0 equals to 0 plus 0 equals to 0. So I have F1 or 2F1, that is why I multiply through by the half. 2F1 minus F2 plus 8 with 3 to be equals to 0. Then we already saw for the F1. What is the simplified value for F1 here?
16.17.
So 16.17. 16.
0.17.
Okay, so 16.17 or 16.2 Newton. Now we can make that substitution there. So this one will be 2 times 16.17 minus our F2 plus 8 root 3 be equals to 0. So we make F2 the subject. So that will be F2 will be equals to 30. This 4, 2, 3. So 32.34 plus 8 root 3. Okay, so simplify this one and let's also see what we'll get.
What is 6.2?
Come again.
46.2 Newton.
Okay. So this will give you 46.2 Newton. So that is the magnitude of the F1 and then the F2. If you are asked to simplify. So that is how you find those forces. So first, resolve the individual forces to get the X and Y component. Then since the object is at rest, you sum everything to the 0. All right, so we are moving to a different thing, which is work. Energy and then power. Okay, so these three words that you've seen on the screen, they are interrelated: work, energy, and then power. If you take the work and energy, they have the same unit. So how do you understand by the word work in the context of physics? When you say work, what does it mean?
Sir.
When a force moves an object through a distance in the direction of the force.
Correct. So the work is said to be done when the force moves an object through a distance in that direction. We're saying that work is said to be done. So it means that before you can say work is done, there must be a force and then there must be a distance. So if we sat down for the whole day learning, just sitting at one point, in the context of physics, we will say that no, you only become tired, but you've not done anything. Carry a load on your head and you stand at one particular place. You might be sweating, but You are not doing anything. You are doing cos 90 job. Okay. So you must have a displacement. You must have a force. Though you but the weight of whatever you are carrying might be a force, but because you are not able to relocate that weight to any distance, work is not done. Okay. So that is what we want to look at. So we'll first start with the work, as we already started. Then after that, we'll come back to the energy and then power. The energy and the power too are also related. So we're saying that work is said to be done when a force moves an object through a distance in the direction of the force. Okay. So work is related to force and displacement. Over which forces act. So if we consider an object that is located at position A, and then this object is moved along the horizontal path to a new location at position B. So the separation between these two locations is D. Okay. Now the force that is being applied is F to an angle of theta. Okay, so you want to drag this box to this with that force. Okay, so once this box is relocated to B, then you can say that there is a work done. Okay, so we can define our work done as work done is equals to what? Force times what? Distance. So which is force cos theta dot D. Okay, so the work done is a force cos theta dot D. Now one thing you should know is that work is scalar physical quantity. Its SI unit. Unit is joules. Okay. With the SI unit of work is joules. So once you are taking the scalar dot product, that's why you're saying that it's a scalar quantity. Now, so 1 joule is the same thing as Newton meter, because force is Newton, and then distance is measured in meters. So you can also use the Newton meter or the joule. There are instances that there's no microphone sound. Yeah, so there's instances that you can have work done, and then the work can be done in the same direction as the force. So if the body moves the object in the same direction as the force, then we'll have our theta to be 0, and cos 0 is 1. Therefore, the work done will be the force times the distance. So the first instance is that if the work done is in the same direction as the force, that is so if there's a direction D and the force is also in the same way, then we'll have the theta becoming 0 degrees because they are parallel. The angle between parallel lines are 0, and cos 0 degrees is equals to 1. So it means that we can say that the work done from the above expression, we can write our work done as this: F or D. Okay, because the whole of this become 1. So we'll be left what? F D. Okay. Now the second case is that now if the body moves in a direction perpendicular to the force, so if the direction is perpendicular to the direction of the force, so in other words, if this is the force and then the direction is in this way, okay, then the theta will be 90 degrees. Because that is going to be the distance between the force and the displacement. And cos 90 is 0. So therefore, work done will be 0. And therefore, work done is 0. So that's why I said when you carry something heavy on your head and you are standing at one point, it's cos 90 work. So once you have 0 multiplied by anything, that will make it 0. Okay, so that will be 0. Then the last instance is that if the body if the direction is opposite to the force, so for that matter, your angle is going to be 180 degrees. So let's say this is the direction of the force and the displacement is going this way. So this makes 180 degrees angle. So in that case, your work done will be equals to minus FD. Your work done will be minus FD. Will be minus FD because cos 180 will give us -1. So when you calculate for work and you are getting a negative answer of that work, it tells us that the direction of the displacement is opposite to the applied force. That's why you are getting a negative work done. So these are the three cases that you can have work being done. One is work can be done if the force acts along the same side with the direction of the displacement. Two, when the force is perpendicular to the direction of the displacement. And then finally, when it is opposite to the force, or the displacement is opposite to the force. So let's now see the examples that you can have. Yes.
Lisa, why did you choose cos instead of other trig ratios?
Oh, okay. You are choosing cos because that is the appropriate trig ratio that is applied along the horizontal. You see, when you look at the sketch that I did here, you see, this sketch signifies that the block is moved along the horizontal. See, it's being dragged like this. So you are pulling it towards this direction. Okay, so the appropriate trig ratio to be used in this scenario is the cos. If this block was pulling up like this, I wouldn't have been using the cos, but sine. Okay, so sine would have shown that it's a vertical movement or motion, but because I'm dealing with the horizontal, that's why it is cos. In fact, the third one is just a ratio. The tan is not any other thing but just a ratio of the sine divided by the cos. Because if I divide sine by cos, I'll get tan. So, but the major two are the sine and the cos, and one talks about the vertical direction, then the other one the horizontal direction. So since we are dealing with the horizontal motion, so that's why it's appropriate to use the cos. Is that okay?
Okay, sir. Thank you.
Welcome. Okay, so example. So the example, when the displacement is 0, you can just think about any other thing that you're carrying on your head without movement. So that one, your load is perpendicular to your displacement. Then when you talk about the force being 0, that is when you also move a block on a smooth horizontal table. Okay, so once you put a block on the smooth horizontal table, you are not dragging anything. You are not using any force to drag the block. So I don't know whether you've seen what I am saying. See, if the surface is smooth and you put a block, the normal block that we know down. Even a child, a baby, which is like still toddling, can be able to push that block to wherever he or she wants, because there is no friction. There's nothing that will require a force. So for a smooth object, the force is zero, or surface, the force is zero. Now, the force and the displacement are mutually perpendicular. Is when you carry a load on your head. Once the angle is 90 degrees, then you cannot have anything there. Okay, so that is the work done as general. But if we now have a work done on a line can be a rope or something. So we can quantify the magnitude. So in a line, like when you don't have a direct or a straight line, so like maybe we all saw how what is that, ants move before. Now if an ant carries something from one point to another, and you want to try to calculate the work that it is done by carrying that, because the ant doesn't have a straight line path, so you have to try as much as possible to measure the curve, that it has passed through. And so that one we're going to use a line integral to do that, to integrate. So let's say, so we are talking about, like, so that one is not a constant force. We talk about a variable force. Okay, so work done by a variable force. Force, not a constant force. So what we look at is a constant force. But what about if the force is varying? So do you apply this force for some time, you change the force to the hand? So how will you do that? So in that case, we're going to get our force. So let's say this is our force, and this force is against the displacement or the distance. So F as a function of x, and this is our x. Now we have this line. So what we need to do is that we need to find the gradient of this line by dividing into smaller pieces. We need to find the gradient. Yeah. So if this is like xi, then this is a final. So let's say ff. So by look at the smaller boxes here, they are the gradients. You know how to find the gradient of a line. So you will take the small work done. Now, if you look at this area, the shaded portion, the boundary from xi to xf is an area. So you can write that the area is equals to change in A, which is equals to the force as a function of this, multiplied by the change in the x, and then the change in x is xi to xf. So why am I saying that? Is that this is a two-dimensional structure. So you have a rectangle. How do you find the area? Area is always what? Length times what? Breadth. So you say the area is equals to LB, or L times B. So the same way, to find this area, I will take the vertical part, which is the Fx, then times the horizontal part, which is the change, starting from xi to xf. So that would be that. But you can see that this is nothing but what? Work. We say that work is equals to what? F times what? X. That is, or F times D. It's the same thing, just change of variables. Okay. So you see that one there. So we can't now say if you pick small change in W, that is, you are taking a smaller work done here, like this portion. It will be nothing but the force multiplied by that smaller portion that you are considering, which is change in X. Now, if you add these small change work done together, if you add the work done by each smaller box, then we count all of them to the last one. That will give us the entire work done by the shaded portion here. Okay, so we'll now take the work done there. So we can say the work done would be equals to the sum of the work done by the individual lines, boxes there. So that will be taken from xi to xf. That's the limit. We are summing it from the first one to the last one. Then that will now give us the one f of x, then multiplied by the change in the x. So this is not anything. Don't be confused about it. Just tell them about like summing all the smaller work done together to get a bigger or the entire work done. Okay. So we can now presume that if our change in x is approaching 0, then we change the summation to what? An integral. Okay. So that is for a very small change in x. Then this now will now be approaching the integral. So for a small change in x, then we'll now have our work done to be equal to the integral of xi to xf. Then we have f of x. Then our change in x will now be changed to what? The x. So we'll now have our work done. So we are now taking the integration. And the purpose of the integration is when you have a smaller entities that you want to quantify it, you can't pick them one by one to count them. So the last way I was using an example like the sun. If you go to the seaside, you try to fetch the sun, and you want to look at how many particles that are present in the amount of sun that you fetch. You cannot count them one by one to get the total number. So you need to use the method of what? Integration. So assuming that you take a small container and then fetch it. So you have to first of all quantify the container, look at the volume of the container. So if you know the volume of the container and then you fetch it full, then you can say that, okay, this is the amount of sun that I am having. Or better still, if you are able to mark out the space after fetching it on the ground, you are able to mark out that one. You can also tell that how much sun you fetch. Okay, so that is about the purpose of the integration. Okay, so that is how you integrate using a variable and force if a force is changing. So you can also put this in 3D, and I will change anything. It's all the same formalism. So if you have a 3D, you have a line again, and this is a position vector R coming from the origin to that line. Then you have another one because of change, because this is longer than that one. So let's say plus R here, and this is R. So you're taking a point 1 to 2. So this to that point. So let's say P1 and P2 here. So you can do the same thing. You can find, so since there's a curve, you can take the work done be equals to the integral of the curve of f dot r that is now taken from P1 to P2 to P2. So you integrate this and put the limits. So these are what we call the upper and then what lower limits. So we can do that. So you can use it the r. So integral of r1 or r plus to r plus. So that's telling you that you have different locations. Okay. F the R. This still expressed as a work done. So there are various ways of what expressing it. Apart from that, there is nothing difficult about that. Okay, so let's see one example. Then, so a box is pulled. Example. A box is pulled. A box is pulled at a constant speed. At a constant speed across a horizontal surface. A horizontal surface by a horizontal rope. A horizontal rope. If 54 joule, 54 joule of work had been done after the box had moved. Had moved 9 meters. Find the constant resistance motion. Find the constant resistance motion. Okay. So solution, since you are dealing with a rough body, you should know that there will be a friction. Okay, so this is your applied force and this is your frictional force. Now, once the work has been done, it means that there is a displacement. The block has been the box has been reallocated. So our work done or our force, so the force, we have to combine the force equated to the net force. So we take F minus F, small f, to be equals to MA. Because this force is moving this way, and then the other one is moving the opposite way. So we sum all the forces equated to the acceleration force. That's the net force. Okay, so we'll have that. That will be our distance. Now, okay, let's get our data. Then we have what the work if 54 joules, so work is 54, work done is 54, then distance or displacement is 9 meters, and then what again? I think these are the things that we know. So given the a box is called is 9 meters, find the constant resistance through that. Okay, so we state our formula. State our formula that our work done is equals to our force cos theta dot the distance. Okay. Now the displacement and the other one is parallel, so it's theta is what, 0. So this will be equals to, the force is not given, we don't know the force, but this is 54. It's equals to the F cos 0 times 9. Then 54 will be equals to 9F, because cos 0 is 1, divided by 9 by 9. Then our constant force that is able to do the 54 joule work will be 54 divided by 9, 2, that's 18, 36, 45, 50. So that will be 6 times. So 6 Newton. So it means that the force that is able to do the 54 joule work by moving that object through a distance of 9 meters is 6 Newton. So that is the answer. Do we understand?
Yeah.
Okay. Any question, please? So we are supposed to end at 4, eh?
Yes, sir.
Yeah. So since we've not gone for a break, we have ended at 3:50, but it's 3:33. So let's pause here. We'll continue, God willing, next week. I'm tired. Sitting at one place for 4 hours is not an easy job. So our next meeting will be looking at yeah.
I want to say, if you can give us some questions on the same work done, then we'll take it for a break.
Oh, okay.
Okay,
no problem.
Okay, thanks.
So I'll try and get you some sample questions to try your hands on. Okay. But that will not be right now. I have to check through my things and get you some questions. But what we'll be looking at when we meet next week, God willing, will be we'll look at conservative force field. Okay, so that is the next thing we have to look at. But because it's a new thing, that's why I want us to pause there and God will on with it. So try and then also read alongside with your model. You can search online for sample questions and whatever we are doing to try your answer. Any other thing, please, before we bring our class to an end?
Please, can we have the recorded version of this one?
And that one there, it doesn't to me, so it's being recorded by code. I only have my note. So if I send you, you only see it, but the audio will not be part because
The
I'm
first
not the one
meeting.
that I'm not the one that will upload that one. So I can only send you the note, but the audio will not be there.
Okay.
Okay. So if nothing more, then can call it a day. God willing, we
Yep.
meet. Yeah.
Sir, please, can you send us the notes?
Yes, I will.
Okay.
But you people don't have a common platform, so how do we communicate? Because you're supposed to have a platform for only physics. Yeah. So if there is any
I don't know if the
information,
course is
then
available.
I will share it to you direct. Because if I go and put it at the BX Science platform, it will
We
be
have
like a
only physics.
distraction too.
We have only physics platform. Yes.
Some of us are not on it.
Me myself is not even there.
Okay.
I'm only in a platform. Those that graduated, yeah, I don't know whether they are continuing from that. We have physics major there. So that one, that group is still existing. I think it started even like the first batch. It was the first batch that they created that platform, and it's still being used. I don't know, but you people, I'm not seeing anything coming there.
Sir, please, do you have the contact of the course rep?
The contact of the
Course rep for physics.
no, I don't know your general course rate. For your group, I don't know.
I think, Madam Patient, if you can take it and share it to everybody.
So what code normally does is that every course has a general, or the program has a general course rep. Those people that have just graduated for physics, it was having Castro was the general course rep. So if anything, he will speak.
We have
Uh-huh.
arrangement was made for that, but hello? Hello.
Yeah.
I said arrangement was made for the general culture, but we had that now we don't know. We were informed it's one Mohammed, but as of now we don't know who that Mohammed is.
So please, can we have your number so that we add you to the group that we have created for only physics?
Okay, no problem.
Okay, so it's either you mention it for us or you put it on the screen.
This is my contact. So, which one? Let me give you this. So then let me come. I have two numbers at times when I'm writing. I do combine them. So this is 87 85 84 or 0244 87 86. Either of them is on WhatsApp. Okay, so let's call it a day for me. Have a good day.
We are not on the conference call.
Come again.
With those who are not on that common platform, I don't know how do we get it.
So the person that I'm sure the one that
So we contact the administrator for that to send it into the general page for the rest to join.
I think they create community so for the let me see physics major. Let me see whether something is yeah. I think physics major. This is a group. No, you people are not there. If not, that is where
Samuel Bonnie and Kafu are the admins for that group.
Which group?
Physics major.
So then it's different from those that have graduated. Okay, so it means I'm not in that one. Please, if you're using my number, use one. Just use one of them.
Physics major, which of the platforms are you talking about?
No, but you can create it yourself. You can create it yourself. Just create a group for all the physics major.
I think the discussion forum.
Yeah, there was the physics major discussion group.
For that one, other people I think there's one day. Physics, chemistry.
No, there's a physics major group. There's a physics major group, so I have to add you. Yeah, there is a physics major group, so I'll send a link.
Who's the administrator?
It's me, Bonnie, I'm here.
Who?
Bonnie is here. That is a physics major discussion forum.
Mr. Bonnie.
Yes.
All right, then I will leave that for you people to discuss. Okay.
All right, thank you, sir.
Yo, thank you too.
So I'll place my number on the chat so that yes.
No, please
call out your number. It may happen that some of us are not in the group, so we may not even know your number.
Yeah, so I'm placing my number on the chat.
No, you may mention your number.
Okay, 0591
0591
00
00
5337
5337.
37, yes.
Please, the number again, 0591
1005337.
Okay, thank you, sir. Mr. Bonnie.
So
Yeah.
WhatsApp.
All right.
WhatsApp you.
Okay, right now, so that I'll add all of you.
All right, thank you, sir.
Okay.
Yes, Mr. Bonnie.